Okay, partial derivatives. Let's get into them. But before we get into them, I want everyone to notice, my little header up here. I actually printed it out this time. Give me some feedback on it. I've been writing them. This was kind of what I had originally planned, but I don't know. It's kind of weird. Maybe it's too proper. I don't want to be too proper because I'm not a proper guy. But anyways, here we go. Partial derivatives. Okay, and this is how we look at the rate of change on a function of several variables. You usually see it as z equals f of x, y, and w is a function of x, y, and z. And basically, here's a notation, and what you're gonna do, if you want to, and this would be called the partial of x. This is called the partial of y. So if we wanted to go do this, we would use this exact same differentiation rules we've been using all along. It's just that when I take partial with respect to x, I pretend like y is a constant, okay? And vice versa. When I take the partial of y, okay, I pretend like x is just a constant, okay? Let's do some insight here. Say here's a function of x and y, and the z-axis would be coming out of there. Okay. Ooh, here we go. Okay. Well. Okay. So here's a surface. We'll just say it's f of x, y. Who knows what it really looks like? But let's say I want to take the partial with respect to x. So I want to do partial with respect to x. So basically, all that means is I'm taking the derivative, with respect to the direction of the x-axis. Okay, so notice, this kind of thing kind of curves as I go over here. Okay, as I'm trucking along the x-axis, it does, encounter a rate of change. Okay, but at the same time, we don't go anywhere on the y-axis. So like if I remove this for a minute, if I was like looking at, a path right here, well, in the y direction, this thing doesn't change because I'm not moving along the y-axis. I'm only moving along the x-axis. So it can only experience a change over the x-axis. So that's why basically we don't care what y is, we just pretend like it's a constant, and we just plug and chug, okay? So let's just go ahead and actually do this. So if I wanted partial of x, I would write it like that. You could also do a shorthand notation. You could write, big or little f, sub x. Okay, so first term, that's just 2x. That's just business as usual. The second one, well, y is essentially a constant, so the derivative with respect to x right there is the same thing as if like this was a 2 or a 3 or something. Okay, and then y squared, well, that's just completely a constant. That'd be just like 4 or something, so that's just 0. Okay, so in our case right here, the partial of x is worth 2x minus y. Okay, and why don't we just go ahead and knock out the partial with respect to y while we're at it. I'll use the other type of notation. Well, here's our original function. So this time the x squared is just a constant, so the derivative of that is 0. Derivative with respect to y, well, that's just negative x. Okay, and then it's just business as usual, 2y. So this one would be equal to, let's go ahead and write it like that. Okay, so these aren't too bad at all, okay? And in my later videos, we'll do some more examples, and we'll get it. There's an actual limit definition of it, but you really don't use that definition too much. This is pretty much the main deal. So let's do another one. Let's go f of x y is equal to, I don't know, let's go 2x let's raise that to a third. So what are we going to do? So let's take, with respect to x, so what am I going to do? I'm just going to go ahead and do the chain rule. So it's just business as normal, okay? Oops, that's a 2. All right, cool. And then we're going to do the inside. Well, derivative with respect to x, that's just 2. And 3y, I mean 3 times y is a constant, so 3y is also a constant. So we're pretty much left with nothing right there. So okay, so that's your partial with respect to x. And let's use a different color for partial against y. Ooh, this is a sharp marker. These things wear down really quick. I mean, I'm just kind of, this paper, I mean, is abrasive. Okay, so against x, well, or against y, x does not change, so it's just a constant. It's ready to change to 0. However, we do have a -3 here. Okay, it looks like, yeah, -3. So partial y is worth -9 2x minus 3y squared. Okay, so let's see here. What do we got? What do we got? Let's go. Let me see if I have time to sneak one in. I might only have time to sneak this one. And okay, so this one right here isn't this isn't too much of a big deal, but I'm just gonna go ahead and I'm gonna use the product rule. Okay, and I pretty much write this thing out every single time I do it. So here we got that, and so what do we got? We got regular g. I think I only have time in the video to go partial x. So it's just regular g times the derivative of f with respect to x is just 1. So we'll just leave that. Then it's just, you know, regular f as in, you know, the top function. Hope I didn't, you know, confuse anyone over here. This is just f is top, g is bottom. And then g prime, which would be the derivative of the bottom, well, that would be just y. And then we just square the bottom. I mean, it's up to you if you want to simplify this anymore. I'm perfectly cool with it, but you know, as math teachers. So there you go. There is partial x, and I think we're just about running out of time. So there are second derivatives. There is implicit differentiation. There are minima, maxima, and you know that limit definition that we're going to get to as well. So I got plenty more videos coming. I'll see you then.